Good evening, astronauts. In the boundless expanse of space lies something that can make any earthly nightmare seem surprisingly gentle and harmless. We're talking about a supermassive black hole, 40 billion times the mass of our Sun, which daily devours the equivalent of an entire star. At the same time, another cosmic giant mercilessly hurls so-called runaway stars into surrounding space, racing at millions of miles per hour like celestial bullets. These phenomena are not the product of distant fantasies or fiction. On the contrary, they are real and terrifying threats that exist in our universe right now. Today, we will journey to the most terrifying black holes ever discovered by humanity. We will discuss stellar corpses capable of stretching your body into spaghetti in mere seconds, as well as galactic titans that can swallow our entire solar system and still crave more. You will witness the very fabric of time bend and tear, matter heating to temperatures exceeding the sun's surface, and gravitational forces reaching such extreme intensity that they literally rip reality apart. Prepare yourselves. We are beginning our descent into the abyss. Imagine a place where the fundamental laws of physics you rely on daily completely break down and cease to operate. Black holes represent the ultimate cosmic nightmare because they defy every one of our survival instincts. You cannot escape them. You cannot hide from them. Once you cross the invisible boundary known as the event horizon, even light itself loses the ability to escape. Imagine it as falling off the edge of a waterfall that stretches infinitely downwards. Only instead of water, you are plummeting through the very fabric of space-time. What makes these objects so fundamentally terrifying is their effect on matter. A black hole forms when a massive star collapses under its own gravity, compressing all its colossal mass into a space smaller than an average city. The result of this process is the creation of a gravitational field so intense that it warps reality itself around it. Picture space as a stretched rubber sheet, and the black hole as a bowling ball placed on that sheet, creating a deep depression into which anything nearby rolls. But here's what's truly chilling. Black holes are not rare cosmic oddities. Scientists estimate that our galaxy alone, the Milky Way, contains 100 million black holes, most of which are stellar mass monsters, 5 to 50 times heavier than our Sun. They lurk in the darkness between stars, invisible to direct observation, except for their gravitational effects on nearby matter. The horror intensifies when you realize how black holes devour matter. As matter spirals towards the event horizon, it heats up from friction, glowing brighter than entire cities. This accretion process creates an accretion disk, a swirling vortex of superheated gas that can extend for millions of miles. Temperatures here exceed 10 million degrees Fahrenheit, hot enough to strip electrons from atoms and create a plasma inferno that would instantly vaporize any known material. Even more disturbing is how black holes manipulate time itself. As you approach the event horizon, time slows down dramatically compared to the outside universe. To someone observing from a safe distance, you would appear frozen at the edge, your image dimming as the light from your body stretches to ever longer wavelengths until it completely vanishes. Meanwhile, you would experience time normally, falling towards the singularity at the center. The singularity itself represents a complete breakdown of our understanding of physics. Here, all the black hole's mass is concentrated into a point of infinite density, where the curvature of space-time becomes infinite. Scientists cannot describe what happens at this point because our equations simply cease to work. What makes this even more unsettling is that black holes are not merely destructive forces. They play a crucial role in the formation and evolution of galaxies, residing at the centers of almost every major galaxy like cosmic engines. The monster at the heart of our own Milky Way galaxy weighs 4 million times more than our Sun. The stellar graveyard around us holds horrors beyond imagination. Every black hole begins as a star, but not just any star. Only the most massive giants, those at least 8 times heavier than our Sun, can create these cosmic monsters. When such a star exhausts its nuclear fuel, it faces a catastrophic end. The core collapses in less than a second, rebounding in a supernova explosion so powerful it can outshine an entire galaxy for months. What remains after this grand stellar demise is a chilling cosmic corpse, inherently more dangerous than the living star ever was. Its core, compressed to unimaginable densities that defy all understanding, transforms into a black hole. To envision this density, imagine the entire mass of Mount Everest condensed to a size smaller than a single grain of sand. This only gives a rough idea of the astounding density we're dealing with. These stellar mass black holes typically have masses ranging from 5 to 50 times that of our Sun, yet occupy a space smaller than most major cities. The event horizon of a black hole 10 times the Sun's mass is only about 60 meters in diameter. Nevertheless, this infinitesimally small region of space generates a gravitational field so intense that it can tear apart anything that dares to approach too closely. The most terrifying aspect of stellar mass black holes is their abundance and startling proximity to us. Scientists have currently identified about 50 confirmed or suspected stellar mass black holes exclusively within our own galaxy. However, theoretical models suggest there could be up to 100 million scattered throughout the Milky Way. They drift through the vast expanses of space like invisible predators, detectable only when they interact with neighboring matter. The closest known black hole to Earth is only 1,500 light-years away, in the constellation Telescopium. This monstrous object, designated HR 6819, weighs approximately 8 times our Sun. While this distance may seem comfortably far, on a cosmic scale, it's practically in our cosmic neighborhood. Most stellar mass black holes remain hidden in the impenetrable cosmic darkness, but some reveal their presence through their feeding habits. When a black hole has a companion star, it can slowly siphon matter from its stellar neighbor. The stolen gas spirals into the black hole, forming an accretion disk that emits intense X-rays. These X-ray binary systems appear as flickering points of light, betraying the presence of the invisible monster. The feeding process creates a truly cosmic dance of destruction. The companion star, typically an ordinary star like our Sun, gradually loses mass as the black hole strips away its outer layers. Over millions of years, the black hole can completely consume its partner, leaving behind only the gravitational perturbation of its own presence. Perhaps most unsettling is how stellar mass black holes can remain active for trillions of years. Unlike stars, which burn out and die, black holes only grow stronger over time. Every particle they consume increases their mass and expands their event horizon, making them even more perilous to anything that dares to come too close. Your body is turned into noodles, stretched beyond recognition in the most horrific way imaginable. Spaghettification represents one of the most vivid horrors that black holes inflict upon matter. The process begins innocently enough as you approach the event horizon, but quickly escalates into a physics nightmare that tears apart everything it touches. The very name comes from how objects are stretched into thin, elongated shapes resembling strands of spaghetti. The horror starts with a simple fact about gravity. It weakens with distance. This means that if you are falling feet first towards a black hole, the gravity pulling on your feet will be significantly stronger than the gravity pulling on your head. For a stellar mass black hole, this difference quickly becomes extreme. Imagine yourself 6 feet tall, falling towards a black hole 10 times the mass of our Sun. When you are about 400 meters from the event horizon, the gravitational difference between your head and feet will be equivalent to hanging a 360-kilogram weight from your ankles. Your body begins to stretch as tidal forces overcome its structural integrity. The stretching intensifies as you get closer. At 200 meters from the event horizon, the differential force increases to several thousand pounds. Your bones begin to crack under the strain. Your muscles tear. Your organs distort beyond recognition. The process is not quick or merciful, but gradual and relentless. However, spaghettification is not limited to longitudinal stretching. As a body undergoes vertical elongation, it simultaneously experiences compression in the horizontal plane. The same tidal forces that mercilessly stretch an object from head to toe also relentlessly squeeze it from side to side. One can imagine being passed through a kind of cosmic pasta machine that stretches you, making you longer and thinner. The mathematical description of this process is as terrifying as the immediate experience itself. For a human body caught in the immediate vicinity of a black hole with a mass of 10 solar masses, the stretching force increases approximately 6 million times compared to what one would experience on Earth. No known biological material can withstand such extreme stresses. The body will literally be torn apart at a molecular level, transforming into a stream of elementary particles. Different types of black holes produce different variations of the spaghettification experience. Less massive black holes are actually more dangerous because their tidal forces manifest with greater intensity near the event horizon. A black hole with 3 solar masses would spaghettify any object long before it could reach the event horizon, whereas a supermassive black hole might allow you to cross the event horizon while still intact. This process affects not only living organisms. Spacecraft, asteroids, and even entire planets would undergo spaghettification if they approached a black hole within a critically short distance. The only difference lies in the distance at which this stretching begins. Larger objects begin to feel these effects at a significantly greater distance, as the gravitational difference across their larger dimensions becomes noticeable much earlier. Scientists have actually observed the phenomenon of spaghettification in action as black holes tear apart stars. These tidal disruption events create truly spectacular displays of cosmic violence, as stellar material is stretched into long, superheated streams of hot gas. To cross this invisible, fateful line is to metaphorically sign one's death warrant in the most absolute way possible. The event horizon represents the absolute point of no return in the universe. This invisible boundary surrounds every black hole like a spherical cage woven from the most warped space-time itself. From the outside, it appears as nothing more than empty space. However, crossing it seals one's fate more completely than any prison ever could. The name itself reveals the full horror of the situation. It marks the horizon beyond which no events can ever be observed by the external universe. Once one crosses this boundary, they are forever cut off from the rest of reality. No signal, no light, no information of any kind can escape to tell the universe what happened to them. For a stellar mass black hole weighing 10 times our Sun, the event horizon is located approximately 96 kilometers from its center. This may seem like a reasonable distance, but the gravitational field here is so intense that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. What makes this trap so insidious is how normal everything feels as you approach it. One might see the event horizon approaching, but they will feel nothing special when crossing it. There is no wall, no barrier, no sensation of passing anything significant. One simply falls through empty space that happens to be warped in the most extreme way. The true horror becomes evident when one tries to communicate with the outside world. As they approach the event horizon, any light they emit becomes increasingly redshifted, meaning its wavelength is stretched to longer and longer values. For observers watching from a safe distance, the person would slow down and gradually disappear. Their image would freeze at the very edge of the event horizon as the light from their body stretches into complete invisibility. Meanwhile, the person themselves would perceive time absolutely normally. They would observe the universe outside the black hole dramatically accelerating as they fall. Stars would be born and die in what would seem like moments. Galaxies would evolve and undergo changes. The cosmic microwave background radiation would blue shift to higher and higher energies, eventually transforming into a lethal stream of gamma rays that would incinerate any living creature. The event horizon also represents the boundary where the curvature of space-time reaches such an extreme degree that straight lines, in the usual sense, cease to exist. Every conceivable path through cosmic space inexorably leads to the singularity located at its very center. Even light rays, which ordinarily propagate in a straight trajectory, here follow curved paths, irrevocably spiraling inwards. Perhaps most unsettling is the realization that the event horizon does not have a fixed size. Every tiny particle absorbed by a black hole slightly increases its mass, which in turn causes the event horizon to expand outwards. A black hole literally grows in size with every portion of matter it consumes, becoming increasingly dangerous to anything that dares to approach it. The event horizon is far more than just a physical boundary. It marks the edge of knowable reality, the point where the familiar laws of physics begin to completely break down. At the heart of every galaxy lurks a beast so massive it defies human comprehension. Supermassive black holes represent an entirely different category of cosmic horror. These monsters possess masses not just tens of times greater than our Sun, but millions or even billions of times. They reside at the nuclei of galaxies, acting as gravitational anchors. Their colossal influence extends for hundreds of thousands of light-years, shaping the very structure of their cosmic neighborhoods. The smallest supermassive black holes contain a mass equivalent to 100,000 suns, compressed into an area smaller than our solar system. The largest discovered to date weighs over 100 billion solar masses, enclosing more matter than the entire Milky Way galaxy. These giants make stellar mass black holes seem like the tiniest specks of cosmic dust. What makes supermassive black holes truly terrifying is not just their gigantic size, but also their insatiable hunger. As they consume matter, they generate some of the most violent and powerful phenomena in the universe. Matter falling into these monsters accelerates to incredible speeds, heating to temperatures of millions of degrees. The resulting accretion disk can outshine billions of stars, creating quasars that we can observe from the most distant corners of the universe. The process of matter accretion creates a truly hellish environment around the black hole. Gas and dust spiral inwards at near light speed, rubbing against each other with such colossal force that they emit intense radiation across the entire electromagnetic spectrum. X-rays, gamma rays, and radio waves erupt from the accretion disk, with energies capable of sterilizing any planet within thousands of light-years. The gravitational influence of these monsters extends far beyond their event horizons. A supermassive black hole can gravitationally bind entire star clusters, causing thousands of stars to orbit around it in dense formations. Some of these orbital velocities reach thousands of miles per second, creating cosmic hurricanes of stellar material. Perhaps most disturbing is how supermassive black holes apparently control the growth and evolution of their host galaxies. Observations demonstrate a close correlation between the mass of a galaxy's central black hole and the mass of its central stellar bulge. In some incomprehensible way, these monsters regulate star formation throughout their galaxy, acting as cosmic thermostats that control the temperature and density of galactic gas. The event horizons of supermassive black holes can span distances exceeding the size of our entire solar system. The black hole located at the center of the Messier 87 galaxy has an event horizon with a diameter of about 24 billion miles. The orbits of all the planets in our solar system could easily fit within this region, with significant space remaining. The most unsettling aspect of supermassive black holes is their apparent immortality. While stellar mass black holes eventually evaporate through a process known as Hawking radiation, supermassive black holes are so colossal that they would take longer than the age of the entire universe to completely evaporate. They are eternal cosmic predators that will outlive stars, planets, and perhaps the universe itself. 26,000 light-years away, at the very heart of our galaxy, lurks a behemoth ceaselessly watching over us. This monster, known as Sagittarius A, occupies the central position in the Milky Way, like a cosmic spider spinning its web. Its mass exceeds that of our Sun by more than 4 million times. This supermassive black hole, our closest galactic neighbor, carries the potential for absolute destruction. Its influence extends throughout the galaxy, affecting every star, every planet, and perhaps every living creature within hundreds of thousands of light-years. This behemoth hides behind dense veils of gas and cosmic dust that completely obscure it from direct observation in the visible light range. Nevertheless, astronomers meticulously track the movements of stars orbiting this invisible monster, recording how they accelerate to incredible speeds as they sweep past the black hole's event horizon. Some of these celestial bodies reach speeds exceeding 5,000 miles per second, moving so rapidly that they could cross the entire United States of America in less than 1 second. One such star, designated S2, follows such an extreme orbit that it passes within just 8 billion miles of the black hole's event horizon. During its closest approach, this star experiences time dilation and gravitational redshift effects that are strong enough to provide a true test for Einstein's theory of general relativity. The light emitted by the star is stretched to longer wavelengths as it climbs out of the black hole's gravitational well, thereby providing direct evidence of this cosmic monster's terrifying power. Sagittarius A's event horizon extends approximately 24 million miles across, which is roughly equivalent in size to Mercury's orbit around the Sun. Within this invisible boundary, the laws of physics as we know them cease to apply. Matter, energy, and any information vanish forever into a space where the concepts of time and space lose all meaning. A particularly disturbing circumstance is the current state of Sagittarius A, which remains relatively quiescent. Unlike many other galactic centers, Sagittarius A is not actively consuming large volumes of matter. It is in a kind of dormant state, only occasionally flaring with bursts of radiation when small portions of gas fall into its accretion disk. However, this state of quiescence cannot last forever. Scientists regularly record periodic flares in the black hole's vicinity, suggesting that it occasionally consumes asteroids, comets, or small gas clouds. Each such feeding event triggers a brief but intense burst of radiation that can be detected across various wavelengths. These flares serve as a reminder that the cosmic monster is still alive and dangerous. The black hole's gravitational influence extends far beyond its immediate surroundings. It plays an important role in stabilizing the orbital movements of stars throughout the galaxy, but it also poses a long-term threat to our solar system. As the Milky Way evolves over billions of years, changes in galactic structure could potentially alter our orbit around the galactic center, bringing us closer to the central black hole. Perhaps most unsettling is the realization that Sagittarius A has the potential to become active again. If a large gas cloud or even another star were to fall into its accretion disk, the release of colossal energy could sterilize significant portions of the galaxy with intense radiation. Black holes can eject stars into space, transforming them into cosmic nuclei flying at millions of miles per hour. The discovery of hypervelocity stars is one of the most terrifying revelations about black hole behavior. These stellar projectiles hurtle through space at speeds exceeding 1,000 miles per second, fast enough to overcome the gravitational pull of entire galaxies. They are the ultimate cosmic bullets fired by supermassive black holes with enough energy to destroy everything in their path. This process begins when a binary star system approaches too close to a supermassive black hole. The intense gravitational field tears the two stars apart in a violent cosmic dance. One star is captured and spirals into the black hole's accretion disk, while its companion is flung away at incredible speed. This can be imagined as a cosmic slingshot effect, but with energies that dwarf anything we can conceive. The most striking and extreme example discovered to date is a star named S5HVS1, which is hurtling through space at a speed exceeding 1,700 miles per second. This celestial projectile moves so rapidly that it could traverse the entire diameter of planet Earth in less than 8 seconds. This star originated from the central black hole of our galaxy and has been on its journey for over 33 million years, covering a distance of almost 200,000 light-years during that time. What makes these hypervelocity stars particularly alarming is their prevalence. Scientists have already identified dozens of confirmed hypervelocity stars, with hundreds more candidates awaiting detailed verification. Each one is a testament to a powerful and violent ejection from a supermassive black hole, suggesting that these cosmic weapons regularly fire shots across the universe. Recent scientific discoveries have revealed an even more disturbing prospect. Some hypervelocity stars, it turns out, originate not from the center of our own galaxy, but from the Large Magellanic Cloud, a neighboring galaxy. This circumstance suggests that the supermassive black hole located in that galaxy has been directing stellar projectiles towards us for millions of years. It appears that we may be at the epicenter of an intergalactic shooting range. The danger posed by hypervelocity stars extends beyond their incredible speed. These stellar projectiles are capable of disrupting the gravitational balance of star systems they pass through, potentially ejecting planets from their stable orbits or directing comets and asteroids onto collision courses. A hypervelocity star passing within a few light-years of our solar system could gravitationally perturb the Oort cloud, sending an entire swarm of comets towards the inner solar system. The very existence of hypervelocity stars also demonstrates the astonishing precision of black holes' destructive power. The gravitational interactions required to accelerate a star to such colossal speeds while maintaining its integrity demand an almost perfect balance of forces. Too little energy, and the star would remain gravitationally bound to the galaxy. Too much energy, and the star would be completely torn apart. Perhaps most unsettling is the realization that for every hypervelocity star we can observe, there may be countless darker objects hurtling through space at similar speeds. Failed stars, rogue planets, and stellar debris. All these objects could be moving at hypervelocity speeds, remaining invisible until they interact with something else. Watch in horror as black holes slowly and agonizingly destroy entire stars. Tidal disruption events represent some of the most spectacular and simultaneously terrifying displays of black hole violence in the entire universe. These cosmic executions occur when a star approaches too close to a supermassive black hole and is torn apart by the same tidal forces that can turn a human body into spaghetti, but on a stellar scale that defies human imagination. This process begins when a star drifts within the tidal radius of a supermassive black hole. For a star like our Sun, approaching a black hole with a mass of 1 million solar masses, this critical distance is approximately 100 million miles from the event horizon. At this point, the gravitational difference between the near and far sides of the star becomes stronger than the star's own gravity, which holds it together. The star does not die instantly. Instead, it undergoes a slow and agonizing destruction that can last for months or even years. The black hole's tidal forces stretch the star into an elongated shape, pulling material from both its ends, while the star's core desperately tries to maintain its structural integrity. Stellar material is drawn into long streams of superheated gas that wrap around the black hole like cosmic spaghetti. As the disrupted stellar material spirals into the black hole, it heats to temperatures exceeding 100 million degrees Fahrenheit. Friction between the different layers of falling gas forms an accretion disk that glows with the intensity of billions of suns. This uncontrolled consumption can outshine an entire galaxy for months, creating a beacon of destruction visible from billions of light-years away. The most disturbing aspect concerning tidal disruption events is their astounding efficiency. Approximately half of the stellar matter is inevitably consumed by the black hole, while the remaining half is ejected into space at incredible speeds. This ejected material can reach speeds of thousands of miles per second, forming expanding shells of hot gas. Such shells could completely sterilize any planetary system within tens of light-years. Scientists have actually observed these cosmic executions of stars in real time using powerful space telescopes. In 2019, astronomers witnessed a tidal disruption event in a galaxy located 650 million light-years away. A star comparable in size to our Sun was methodically torn apart over several months, while telescopes meticulously recorded the entire process across multiple wavelengths of light. What makes these phenomena particularly terrifying is their frequency. Astronomers estimate that tidal disruption events occur in any given galaxy approximately once every 10,000 to 100,000 years. Given that there are billions of galaxies in the observable universe, this means that stars are being torn apart by black holes somewhere in space every few seconds. The radiation emanating from tidal disruption events can be detected over vast distances, suggesting that these stellar agonies produce some of the brightest flares in the entire universe. The energy released during one such event can be equivalent to the total energy produced by our Sun over its entire 10 billion-year lifespan. Welcome to the most violent place in the universe, where matter perishes with a furious scream. The accretion disk surrounding an insatiable black hole is a true hell materialized in space. This rapidly rotating vortex of superheated matter creates such extreme temperatures and pressures that the familiar laws of physics completely cease to apply. Here, atoms are stripped of their electrons, molecules break down at a subatomic level, and matter itself undergoes unthinkable torture, transforming into forms that cannot exist anywhere else in the universe. The disk forms when matter rushes towards a black hole, but possesses too much angular momentum to fall directly in. Instead, the material spirals inward, like water going down a cosmic drain. However, this drain leads to complete oblivion. As matter orbits closer and closer to the black hole, it accelerates to incredible speeds, sometimes reaching 30% of the speed of light. Friction between the different layers of the disk generates temperatures that exceed the temperatures of stellar cores. The inner regions of the disk heat up to temperatures exceeding 1 billion degrees Fahrenheit, hot enough to fuse any element in the periodic table. At such temperatures, matter exists in a plasma state, where electrons are completely separated from atomic nuclei, forming a kind of soup of charged particles that glows with an intensity equal to trillions of suns. The disk extends outward from the region immediately outside the event horizon to distances that can span several light-years. The outer regions remain relatively cool, only a few million degrees, but even these cold zones would instantly vaporize any known material. The temperature gradient across the disk creates a hellish rainbow of electromagnetic radiation, from radio waves in the outer regions to gamma rays near the center. What makes accretion disks truly terrifying are their magnetic fields. Rotating charged particles generate magnetic field lines that twist and tangle under the disk's rotation. These magnetic fields can become so intense that they launch jets of plasma at near light speed, creating cosmic flamethrowers that can extend for millions of light-years. The disk's rotation gives rise to a phenomenon known as frame dragging, with a black hole's rotation literally drags spacetime along with it. This effect becomes so powerful near the event horizon that nothing can remain stationary relative to distant observers. Even light, which usually travels in straight lines, follows curved paths that inexorably spiral inward. The incredible violence within accretion disks surpasses all conceivable limits of human imagination. Matter involved in this cosmic dance is exposed to gravitational forces millions of times greater than Earth's gravity. The resulting accelerations are capable of shattering any solid object into individual atoms, and the radiation fields are intense enough to strip electrons from atoms at a molecular level, transforming matter into ionized plasma. Perhaps the most striking and simultaneously frightening aspect is the disk's extraordinary efficiency as a cosmic furnace. While nuclear fusion occurring in the hearts of stars converts less than 1% of matter into energy, accretion disks can transform up to 40% of infalling matter into pure energy. This makes them the most powerful and efficient energy generation mechanism in the entire universe. In the immediate vicinity of a black hole, time itself becomes an instrument of psychological torture. Time dilation, or gravitational time dilation, is one of the most mind-bending and terrifying aspects of black hole physics. As you approach the event horizon, time slows down relative to the outside universe in a way that would inevitably drive any conscious being in such a situation insane. This phenomenon is not science fiction, but a solid physical reality, a direct consequence of Einstein's theory of general relativity, which transforms time from an immutable constant into a variable capable of causing nightmarish sensations. This effect begins to manifest subtly as you approach the black hole. At a distance of 10 event horizon radii, time flows only slightly slower than normal. However, as you approach further, time dilation becomes more pronounced. At 3 event horizon radii, time moves approximately twice as slow as for distant observers. At 2 radii, it slows to 1/3 of its normal speed. The horror intensifies as you approach the event horizon itself. Here, time dilation tends towards infinity. From your internal perspective, you will experience the passage of time normally. But for anyone observing you from a safe distance, your movements will dramatically slow down. They will become sluggish and unhurried. Your voice will drop to lower frequencies, and your image will dim as the light from your body stretches to longer wavelengths. This creates a disturbing and paradoxical effect. You will never see yourself cross the event horizon from an external perspective. Instead, you will appear frozen at the boundary, your image becoming increasingly red and dim until it finally vanishes into invisibility. Nevertheless, from your own frame of reference, you will pass through the event horizon in a finite time and continue to fall towards the singularity, the center of the black hole. The psychological implications of such a phenomenon are staggering. Imagine trying to communicate with someone falling into a black hole. Their messages would arrive at increasingly longer intervals, with each transmission redder than the last. Eventually, their words would be stretched into radio waves, then infrared, until their communication disappears beyond detection, completely severed. Even more disturbing is what you would experience during the fall. As you approach the event horizon, you would see the universe outside the black hole dramatically accelerate. Stars would be born and die in what would seem like moments. Galaxies would evolve and change before your eyes. The cosmic microwave background radiation would blue shift to higher energies, eventually transforming into a stream of lethal gamma rays, bringing doom. The time dilation effect creates a one-way information barrier. Light signals from the external universe can reach you, but your signals cannot reach the outside. You find yourself in a kind of temporal prison, where you can watch the universe age around you, but you cannot communicate with it, remaining completely isolated. Perhaps most unsettling is the realization that time dilation affects not only your perception, but also your biological processes. Your metabolism, brain functions, and cellular repair mechanisms slow down from an external perspective. You would age slower relative to the external universe. But this seeming gift comes with the ultimate price of complete isolation from the rest of reality, stripping you of all connection to the outside world. Time dilation near black holes vividly demonstrates that time is not a constant, as we are accustomed to thinking, but a flexible dimension that can stretch and contract under the influence of gravity. Deep in the constellation Canes Venatici hides a monster that weighs more than our entire galaxy. Imagine how grand our entire galaxy is, yet even it pales in comparison to cosmic monsters. The object known as Ton 618 truly embodies the apotheosis of cosmic horror. It is a hyperluminous quasar, powered by a supermassive black hole. Its mass is so colossal that it challenges all our current notions of how such behemoths can even form and exist in space. This cosmic giant surpasses the mass of our Sun by more than 40 billion times, rightfully earning it the title of one of the most massive objects ever discovered in the vast universe. These figures alone are capable of causing profound shock. The event horizon of this monstrous object extends for almost 800 astronomical units. This means that the entire orbit of planet Neptune could easily fit inside it, with plenty of free space remaining. If one could, by some incredible means, travel at the speed of light, it would take them over 6 hours to cross it from one side of the event horizon to the other. However, the true source of horror lies in this black hole's insatiable appetite. Ton 618 consumes matter at a truly incredible rate, devouring the equivalent mass of our entire sun every single day. This uncontrolled consumption gives rise to an accretion disk that glows with such dazzling brightness that it can outshine 400 trillion suns combined. The energy released is so colossal that we can detect it from a distance exceeding 10 billion light-years. The gravitational field around this cosmic giant warps space-time to an almost unimaginable degree. At the event horizon itself, the velocity required to escape is the speed of light. However, the tidal forces here are so intense that they would tear any known material into minute particles long before it could reach this fateful boundary. The gravitational gradient in the immediate vicinity of this black hole is so steep that it could stretch a human body for thousands of miles in mere seconds. What makes Ton 618 particularly terrifying is its venerable age. The light we observe from this quasar began its grand journey when the universe was less than 1 billion years old. This circumstance means that this cosmic monster formed at the very dawn of the cosmos. The question of how a black hole could reach such colossal dimensions so quickly after the Big Bang remains one of the greatest and most intriguing mysteries in modern astrophysics. The accretion disk encircling this black hole creates a kind of cosmic beacon that can be discerned from almost the very edge of the observable universe. The disk itself extends for several light-years, forming a rotating vortex of superheated matter that glows at temperatures exceeding 1 billion degrees. The magnetic fields generated by this disk are so intense that they can launch jets of plasma at near light speed. Ton 618's gravitational influence extends far beyond its immediate vicinity. This cosmic giant could gravitationally bind entire star clusters and even relatively small galaxies, causing them to orbit around it like cosmic moths drawn to a flame. Any star system within thousands of light-years would be subjected to intense tidal forces and lethal radiation. Perhaps most disturbing is the realization that Ton 618 represents only one of many examples of ultramassive black holes that could potentially exist throughout the universe. These cosmic titans challenge our established models of black hole formation and growth, suggesting that the universe may harbor monsters even more terrifying than those we can imagine. At the very heart of the Phoenix cluster lies a black hole that, by some estimates, may weigh 100 billion suns. Phoenix A currently holds the title of champion in the cosmic heavyweight division. This supermassive black hole is so colossal that it expands the very definition of what we thought was possible. Located 5.7 billion light-years from Earth, this cosmic behemoth potentially contains more mass than some entire galaxy clusters, making it the most massive black hole ever discovered. The scale of this object defies human comprehension. With an estimated mass of 100 billion solar masses, Phoenix A weighs more than twice as much as Ton 618 and more than 20,000 times more than the black hole located at the center of our own galaxy. If, by some incredible means, our sun could be replaced by this monster, its event horizon would extend far beyond the orbit of planet Neptune. The event horizon of Phoenix A, that invisible boundary beyond which nothing, not even light, can escape, stretches approximately 1,950 astronomical units. This makes it a truly colossal object, exceeding in size some small star systems. If light, traveling at a dizzying speed of 186,000 miles per second, were to attempt to cross this boundary from one side to the other, it would take over 13 hours. The gravitational field at such a significant distance is so overwhelmingly intense that even a nearby observer would immediately notice clear time dilation effects. What makes Phoenix A particularly awe-inspiring is its central location within the Phoenix Cluster, one of the most massive galaxy clusters known in the observable universe. This grand cluster contains thousands of galaxies, inextricably bound together by a powerful gravitational pull, forming an intricate cosmic web of dark matter and hot gas. Phoenix A, like a cosmic spider, sits at the very heart of this cluster, and its colossal gravitational influence extends for millions of light-years. This black hole appears to be actively consuming the hot gas that pervades the entire cluster. This intergalactic medium, heated to temperatures of tens of millions of degrees, provides an almost inexhaustible supply of matter for this cosmic monster to consume. In the process of such intense feeding, powerful radio jets are generated, extending millions of light-years from the black hole, carving out enormous cavities in the cluster's gas. These cavities, in turn, can be detected by radio telescopes located on Earth. The very formation of such a monstrously massive black hole remains one of the greatest unsolved mysteries of modern astrophysics. Traditional models describing the growth of black holes suggest that significantly more time than the age of the universe itself is required to reach such colossal sizes. Phoenix A, therefore, challenges these established models, forcing scientists to explore entirely new mechanisms of rapid black hole growth that likely operated in the early universe. The gravitational effects of Phoenix A extend far beyond its immediate surroundings. This cosmic giant actively helps regulate the temperature and density of gas throughout the Phoenix cluster, effectively controlling the rate of star formation in thousands of galaxies. Its dominant influence shapes the evolution of the entire cluster, which contains more mass than 10,000 galaxies like our Milky Way. Perhaps most disturbing is the possibility that Phoenix A represents only the tip of the iceberg. If black holes can reach masses of 100 billion solar masses, what can prevent them from becoming even grander? The universe may harbor black holes with masses in the trillions of solar masses, monsters so colossal that they can dwarf entire galaxy clusters. When supermassive black holes actively consume matter, they generate lethal beams capable of sterilizing entire galaxies. Quasars represent some of the most violent and energetically powerful phenomena in the entire universe. Fueled by supermassive black holes that have awakened from dormancy and begun an uncontrolled consumption of cosmic proportions, these monsters create accretion disks whose luminosity is so dazzling that they can outshine their entire host galaxies, becoming beacons of destruction visible from billions of light-years away. The very name quasar comes from quasi-stellar radio source, as these objects initially appeared as star-like points of light in early radio surveys. However, their true nature is far more terrifying and majestic. Quasars are actually the active nuclei of distant galaxies, where supermassive black holes consume colossal amounts of matter and convert it into pure energy through the most efficient process known in the universe. The energy output of a typical quasar surpasses the combined output of 1 trillion suns. The most powerful quasars can be 10,000 times brighter than our Milky Way galaxy, which, incidentally, contains over 100 billion stars. All this colossal energy emanates from matter falling into the black hole's accretion disk, where gravitational forces accelerate the infalling material to speeds extremely close to the speed of light. The accretion disk surrounding a quasar creates a truly cosmic furnace, where temperatures exceed 1 billion degrees Fahrenheit. At such extreme temperatures, matter exists in a plasma state, where atomic nuclei are completely stripped of their electrons. The resulting radiation covers the entire electromagnetic spectrum, from radio waves to gamma rays, creating a stream of lethal energy capable of sterilizing any planet within thousands of light-years. Many of these cosmic objects, known as quasars, are also sources of relativistic jets, narrow, powerful beams of plasma that erupt from the poles of supermassive black holes, reaching speeds exceeding 99% of the speed of light. Such jets can extend for millions of light years, forming a kind of cosmic death ray that pierces intergalactic space like giant laser beams. The energy carried by these jets is equivalent to the combined energy of millions of stars. The radiation emanating from quasars is so incredibly intense that it can completely suppress the process of star formation in their host galaxies. This colossal energy heats and disperses gas clouds that would normally collapse and form new stars, effectively sterilizing the galaxy. This process, known as quasar feedback, can halt star birth for many millions of years, leaving behind a dead galaxy filled only with aging stars. Perhaps the most alarming fact is the realization that quasars were significantly more common in the early history of the universe. Astronomical observations show that the number of quasars peaked when the universe was only a few billion years old, suggesting much greater activity of supermassive black holes at the dawn of the cosmos. This early era represents a period when the universe was literally permeated by these cosmic death rays. The energy radiated by quasars can be detected across the entire electromagnetic spectrum, but their most lethal emissions manifest as high-energy gamma rays and X-rays. These types of radiation can penetrate deep into planetary atmospheres, destroying ozone layers and sterilizing any life forms exposed to their destructive effects. The most terrifying aspect of quasars lies in their unpredictability. A dormant supermassive black hole can suddenly activate if it encounters a new source of matter, transforming a quiet, calm galaxy into a source of cosmic death rays almost overnight. When two black holes begin to approach and spiral towards each other, they generate the most violent events observed since the Big Bang. Mergers of binary black holes represent an absolute cosmic catastrophe. These events are so grand and violent that they shake the very fabric of space-time. Such collisions release more energy in the form of gravitational waves than all the stars in the observable universe produce in light, creating ripples in space-time that can be detected from billions of light years away. The process begins when two black holes start orbiting each other in a deadly dance that can last for billions of years. As they spiral inward, they gradually lose energy through the emission of gravitational waves, leading to the gradual decay of their orbits. The closer they get to each other, the faster they orbit, until in the final moments they begin to move around each other at speeds close to the speed of light. The final merger occurs in a fraction of a second. But the energy released in this brief moment is truly staggering. A typical binary black hole merger converts about 3 solar masses of matter into pure gravitational wave energy. This energy is radiated as ripples in space-time that propagate outward at the speed of light. The gravitational waves resulting from these mergers carry valuable information about the masses, spins, and orbital dynamics of the black holes. When these waves pass through Earth, they stretch and compress space itself by amounts smaller than 100,000th the width of a proton. Nevertheless, despite their incredible subtlety, these waves are evidence of the most violent and powerful events in the universe. The most massive black hole merger ever detected by scientists involved two cosmic monsters of 85 and 66 solar masses respectively. This grand collision created a final black hole of approximately 140 solar masses, meaning that about 11 solar masses of matter were converted into gravitational wave energy in less than 1 second. What makes these collisions truly terrifying is their potential impact on the surrounding environment. The gravitational waves generated during a merger can disrupt the stability of any matter within hundreds of light years, potentially triggering supernovae in nearby stars or ejecting planets from their orbits. The distortions of space-time are so strong that they can create regions where the normal laws of physics temporarily cease to apply. The merger also becomes a source of an astonishing phenomenon called gravitational recoil. When two black holes with different spins collide, the resulting black hole can be ejected from the collision zone at speeds exceeding 1,000 miles per second. This event creates a rogue black hole that rapidly moves through space at hypervelocity, potentially destabilizing any star systems it may encounter in its path. Perhaps the most disturbing aspect is the realization that binary black hole mergers can be a catalyst for the formation of even more massive black holes. The collision can generate shock waves that propagate through nearby gas clouds, triggering gravitational collapse, leading to the formation of new black holes. This process potentially creates a cascading effect, where one merger initiates the creation of multiple new black holes, like a chain reaction. The frequency of these cosmic catastrophes has turned out to be significantly higher than initially assumed. Gravitational wave detectors record binary black hole mergers approximately once a week, indicating the continuous occurrence of these grand and violent events throughout the universe. The universe itself seems to cry out in pain when these colossal cosmic objects collide with each other. Gravitational waves represent the universe's most primordial and fundamental form of communication. They are ripples in the very fabric of space-time that carry messages of cosmic violence, traversing billions of light-years. These waves propagate at the speed of light, causing space itself to stretch and compress as they move through the universe. When they reach our planet Earth, they reveal the existence of cataclysms that occurred in the distant cosmic past. The detection of gravitational waves required the creation of the most sensitive instruments ever invented by humanity. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, uses laser beams to measure changes in distance that are less than 100,000th the width of a proton. This incredible degree of precision allows scientists to detect the faint ripples in space-time created by colliding black holes located billions of light-years away. Every detection of gravitational waves tells a unique story of cosmic destruction. The waves carry valuable information about the masses and spins of the colliding black holes, their orbital dynamics, and the immense energy released during the merger. Scientists can reconstruct the entire collision event from these subtle ripples, observing how two massive objects gradually spiral towards each other and eventually merge in a powerful burst of gravitational energy. The first recorded detection of gravitational waves, designated GW150914, revealed the collision of two black holes with masses of 36 and 29 solar masses, respectively. The merger occurred 1,300,000,000 years ago, in an era when multicellular life was just beginning to emerge on Earth. The gravitational waves from this ancient collision traveled through space for over 1 billion years before reaching our planet. What makes gravitational waves particularly terrifying is their unique ability to carry information about events that would otherwise remain completely invisible. Black holes generally do not emit light, making them undetectable by traditional telescopes. However, when they collide, they generate gravitational waves that can be successfully detected, even if the merger occurs in distant corners of the universe, hidden behind opaque clouds of gas and dust. The energy carried by gravitational waves is truly colossal. A typical black hole merger releases more energy in gravitational waves than all the stars in the observable universe emit in light. This energy propagates outward, taking the form of ripples in space-time, and carries the signature of the collision over vast cosmic distances. The detection of gravitational waves has convincingly demonstrated that black hole mergers occur much more frequently than previously thought. The universe experiences these cosmic catastrophes with astonishing frequency, approximately once per minute, meaning a constant disruption of space-time by the violent death throes of massive cosmic objects. Perhaps most disturbing is the realization that gravitational waves represent only one form of cosmic messenger. The universe could potentially be filled with other forms of space-time perturbation that we have not yet learned to detect. Dark matter interactions, neutron-star collisions, and even the expansion of the universe itself could generate gravitational wave signatures that carry information about phenomena beyond our current understanding. Humanity's ability to detect gravitational waves has opened a completely new page in the book of cosmic existence, allowing us to glimpse the grandest and most violent events ever to occur in the universe. However, this achievement has also revealed the existence of unknown cosmic forces relentlessly shaping reality on its grandest scales. Something incredibly massive and completely invisible is inexorably pulling our galaxy towards an unknown fate. Deep within the so-called zone of avoidance, securely hidden behind the dense disk of our own galaxy, lurks a gravitational anomaly so colossal in its dimensions that it simply defies current scientific explanation. This phenomenon, known as the Great Attractor, represents one of the most disturbing and unresolved mysteries of modern cosmology. It is a region of cosmic space possessing a mass equivalent to tens of thousands of galaxies, yet remaining virtually invisible to our most powerful telescopes. This cosmic giant is located approximately 250 million light-years from us, in the direction of the constellation Hydra. Its gravitational field is so pervasive and powerful that it significantly influences the motion of galaxies located hundreds of millions of light-years away, including our own Milky Way. We, along with our entire galaxy, are moving towards this invisible mass at a speed exceeding 400 miles per second, drawn by a gravitational force that we are not yet able to fully comprehend and understand. The Great Attractor manifests its presence through peculiar and anomalous movements of galaxies in our local region of the universe. According to the well-known Hubble's law, galaxies should be receding from us at speeds directly proportional to their distance. However, numerous astronomical observations demonstrate that galaxies in a vast volume of cosmic space are moving towards the same region, as if being pulled by a colossal, invisible gravitational source. What makes the Great Attractor particularly intriguing and even somewhat terrifying is its hidden nature. This massive object resides behind the so-called zone of avoidance, a region of the sky that is completely obscured by vast concentrations of dust and gas located in the disk of our own galaxy. This cosmic veil effectively hinders our view of what lies beyond it, creating a kind of blind spot in our vision of the universe, where something incredibly massive and mysterious is concealed. Recent astronomical observations, conducted using radio telescopes and X-ray telescopes, have gradually begun to penetrate this cosmic veil, slowly revealing the complex and multifaceted structure of galaxy clusters and superclusters. The Great Attractor appears to be closely associated with the Norma cluster, a massive galaxy cluster that may contain several supermassive black holes. However, the visible matter present in this region cannot fully account for the colossal gravitational field necessary to influence such a gigantic volume of cosmic space. The most disturbing of all possible hypotheses is that the Great Attractor may contain a concentration of dark matter significantly more massive than anything previously discovered by humanity. Dark matter, which is estimated to constitute about 85% of all matter in the universe, interacts exclusively through gravity and remains absolutely invisible to all known forms of electromagnetic radiation. A massive halo of dark matter could, therefore, produce all the observed gravitational effects while remaining completely undetectable by traditional methods. The gravitational influence of the Great Attractor extends far beyond our local group of galaxies. Entire galaxy clusters, each containing thousands of individual galaxies, are being drawn towards this invisible mass, creating a colossal cosmic flow that spans hundreds of millions of light-years. This large-scale movement strongly suggests that the Great Attractor may be only part of an even grander structure that shapes the distribution of matter on the largest scales of the universe. Perhaps the most alarming aspect of this situation is the realization that the ultimate fate of our galaxy may be predetermined by this invisible cosmic monster. As we steadily move towards the Great Attractor, we may eventually be drawn into a region of space where gravitational fields become so intense that they disrupt the very structure of our Milky Way. In the first second after the Big Bang, the universe may have spawned monsters that still lurk in its boundless darkness. Primordial black holes represent the ultimate cosmic horror because they can hide anywhere in the universe, forming not from stellar collapse, but from violent fluctuations of the earliest universe. These ancient monsters could have been created in the first fraction of a second after the Big Bang, making them older than stars, planets, and perhaps even the fundamental particles that make up ordinary matter. For primordial black holes to form, specific conditions of extreme density and pressure were required, which were characteristic exclusively of the primitive universe. Within the first second after the Big Bang, random density fluctuations in matter could have led to the formation of regions so concentrated that they instantly collapsed into black holes, bypassing the star formation stage. These primordial cosmic objects could have had masses ranging from smaller than an asteroid to millions of times the mass of our Sun. What makes primordial black holes particularly terrifying is their potential abundance. Theoretical models suggest that they may constitute a significant portion of the dark matter in the universe. This means that these invisible cosmic entities could significantly outnumber visible stars. They could be hiding in the vast expanses between stars, at the remote edges of our solar system, or even passing through Earth itself. The smallest primordial black holes could have masses comparable to mountains, yet their sizes would be smaller than atomic nuclei. These microscopic cosmic objects are virtually impossible to detect directly, but their gravitational effects could still influence the movement of larger bodies. A primordial black hole passing through our solar system could potentially disrupt planetary trajectories or direct comets and asteroids onto collision courses with Earth. Intermediate mass primordial black holes could pose an even greater threat. These giants could weigh from 1,000 to 100,000 times the mass of our Sun, making them significantly more massive than any stellar black hole, yet smaller than supermassive black holes. If one of these objects were to pass through our galaxy, it could gravitationally disrupt star formation processes, trigger supernova outbursts, or even completely eject stellar systems from the galaxy. The largest primordial black holes could have served as a kind of seed for the supermassive black holes we observe today in the central regions of galaxies. These behemoths would have gained a significant advantage in the cosmic race for growth, potentially explaining how supermassive black holes could have formed so quickly in the early universe. Perhaps most disturbing is the realization that primordial black holes can remain absolutely undetectable until they interact with other matter. Unlike stellar black holes, which often reveal themselves through X-ray emission from accretion disks, primordial black holes formed in the empty space between galaxies would remain invisible until they encountered a source of matter to consume. The search for primordial black holes has become one of the primary tasks of modern astrophysics. These ancient cosmic formations may hold the key to understanding the nature of dark matter, the mechanisms of the first galaxy formation, and the ultimate fate of the universe itself. The universe hides a terrifying population of missing black hole links that we are only beginning to discover. Between stellar mass black holes, formed by the death of stars, and the supermassive giants at the centers of galaxies, there is a mysterious gap, representing one of the most disturbing puzzles in modern astrophysics. Intermediate mass black holes, weighing from 100 to 100,000 times the mass of our Sun, should exist in large numbers throughout the universe. However, they are stubbornly difficult to detect. This missing population is a true cosmic horror story, because these intermediate mass black holes may be hiding in plain sight. Unlike their smaller stellar counterparts, which often reveal themselves through X-ray emissions from companion stars, or their supermassive relatives, which power bright quasars and active galactic nuclei, intermediate mass black holes can remain invisible, lurking in the darkest corners of the universe. The few detected intermediate mass black holes demonstrate the terrifying potential of these cosmic predators. One candidate, designated 3XMM J215022.4, 055108, weighs about 50,000 times the mass of our Sun and is located on the outskirts of a distant galaxy. This cosmic object appears to be slowly consuming a nearby star, creating periodic X-ray flares that betray its presence. What makes intermediate mass black holes particularly dangerous is their potential for mobility. Unlike supermassive black holes, which are firmly fixed in galactic nuclei, intermediate mass black holes are capable of wandering through cosmic space like rogue objects. These cosmic nomads could have been ejected from their original habitats by intense gravitational interactions with other black holes, or due to asymmetric gravitational wave emissions arising from mergers. The formation mechanisms of intermediate mass black holes remain mysterious and alarming. They could have arisen from the direct collapse of the first generation of stars in the early universe, through the merger of multiple stellar mass black holes, or as a result of matter accretion onto primordial black holes. Each of these formation scenarios implies the existence of different populations of such monsters hiding in the boundless cosmic darkness. Perhaps most terrifying is the possibility that intermediate mass black holes may lurk in globular clusters, dense conglomerations of stars orbiting galaxies. These ancient stellar agglomerations contain hundreds of thousands of stars packed into regions only a few tens of light-years across. The gravitational dynamics within these clusters could have facilitated the formation of intermediate mass black holes through stellar collisions and mergers. The detection of intermediate mass black holes would fill the missing link between stellar and supermassive black holes. However, it would also reveal that the universe contains a colossal population of invisible predators that we are only beginning to discover. These monsters could outnumber both stellar and supermassive black holes, creating a hidden ecosystem of cosmic destruction. The search for intermediate mass black holes has significantly intensified with the discovery of gravitational waves, which provide a fundamentally new method for observing black hole mergers throughout the universe. Future gravitational wave detectors are likely to reveal the existence of these missing links of monsters in significant quantities. Black holes, ejected from their galaxies like bullets from a gun, wander through the cosmic darkness. Rogue black holes represent the ultimate cosmic nightmare because they combine the destructive power of black holes with the unpredictability of objects moving at hypervelocity in space. These monsters have been propelled from their original galaxies by violent gravitational interactions, creating cosmic wanderers that traverse the universe at speeds exceeding 1,000 miles per second. The ejection process begins when supermassive black holes collide with other massive objects. At the moment two galaxies merge, their central black holes can engage in a complex gravitational dance that sometimes leads to the ejection of one or both black holes from the newly formed galaxy. The gravitational slingshot effect can accelerate these monsters to speeds sufficient to completely escape their host galaxy. The most terrifying aspect of rogue black holes lies in their invisibility. Without hot accretion disks that make feeding black holes visible, these cosmic wanderers drift in intergalactic space as absolutely dark objects. They can only be detected if they pass in front of background stars, creating transient gravitational lensing phenomena that warp and amplify starlight. Scientists hypothesize that billions of rogue black holes may be wandering through the universe, ejected from their galaxies during the violent merger processes that shaped cosmic structure over billions of years. These monsters carry the gravitational memory of their turbulent past, traveling through space like cosmic nuclei launched by galactic collisions. The danger posed by rogue black holes extends far beyond their immediate destructive power. A rogue black hole passing through our galaxy could gravitationally disrupt the orbits of stars, potentially ejecting some star systems entirely from the galaxy. If a rogue black hole were to pass through the outer regions of our solar system, it could disturb the Oort cloud, directing a swarm of comets towards the inner solar system. The detection of these elusive rogue black holes, or cosmic wanderers as they are also called, has been significantly aided by the development of gravitational wave detectors. These highly sensitive instruments are capable of picking up the echoes of black hole mergers occurring in the most distant corners of the universe. Among the many recorded collisions, some may well involve rogue black holes that have wandered through the vast expanses of space for billions of years before encountering other massive celestial bodies. Perhaps the most disturbing aspect is the realization that rogue black holes may be far more common than we initially assumed. The violent and powerful processes that generate these cosmic nomads were likely actively at play from the earliest stages of the universe's existence, when the processes of galaxy formation and their subsequent mergers were significantly more frequent phenomena. This suggests that intergalactic space may be literally filled with countless invisible predators, posing a hidden threat to cosmic life. The phenomenal speed of rogue black holes makes them particularly dangerous. Moving at speeds reaching 1,000 miles per second, these cosmic monsters could cross the entire solar system in a matter of months. Their approach would be virtually imperceptible until they began to exert a noticeable gravitational influence on nearby objects. This would leave extremely little time for any countermeasures or preparation. Thus, the very existence of rogue black holes radically changes our traditional understanding of cosmic safety. Space ceases to be an empty void and appears before us as an arena filled with invisible monsters that can appear from any direction at any time. Beyond rogue black holes, some of their counterparts can create lethal beams extending 1,000,000 light-years, capable of sterilizing entire regions of the universe. These relativistic jets represent perhaps the most destructive weapon available in the cosmic arsenal. They are streams of plasma accelerated to 99% of the speed of light by incredibly powerful magnetic fields generated around rapidly rotating black holes. These cosmic flamethrowers can extend for millions of light-years, carrying enough energy to power entire galaxies and creating zones of total destruction that persist for millions of years. The formation of these colossal jets begins with the rotation of the black hole itself. As this cosmic monster rotates, it drags the surrounding space-time along with it, giving rise to a phenomenon known as frame dragging. This rotation, combined with the powerful magnetic fields generated by the accretion disk, creates a kind of cosmic dynamo that accelerates charged particles to relativistic speeds. As a result, jets are ejected from the black hole's poles as two narrow beams, maintaining their coherence over incredible distances. Particles moving within these jets travel at such colossal speeds that they experience extreme relativistic effects, including time dilation and length contraction. From the perspective of the particles themselves, a journey of millions of light-years occurs in significantly less time due to these astonishing relativistic effects. The energy carried by these jets is truly staggering. A typical galactic jet carries more energy than the combined output of billions of stars, with all this energy concentrated in a beam only a few thousand light-years wide. This energy density is so high that it can heat intergalactic gas to temperatures exceeding 100 million degrees Celsius, thereby creating cavities in the cosmic web that can be detected by X-ray telescopes. What makes these jets particularly terrifying is their ability to influence entire galaxy clusters. When a jet collides with the hot gas filling the space between galaxies, it generates shock waves that propagate outward for thousands of miles. These shock waves can stimulate star formation in some regions while completely suppressing it in others, thereby effectively controlling the evolution of galaxies over millions of light-years. Jets also create so-called radiolobes, massive regions of space filled with high-energy particles that emit radio waves. These lobes can be larger than entire galaxies and persist for millions of years even after the jet's activity ceases. Any planet or star system caught within these radiolobes would be bombarded by lethal radiation capable of sterilizing all life forms. Perhaps the most disturbing aspect is the directionality of this cosmic weapon. Although jets are narrow and focused, they can change direction as the black hole's rotation axis precesses over time. This means that regions of space previously considered safe from the jet's lethal radiation could suddenly find themselves in the line of fire, subjected to destructive effects. The detection of these colossal jets, extending over 100 million light-years from their originating black holes, vividly demonstrates the incredible reach of this cosmic weapon. Such ultra-long jets are capable of actively influencing the fundamental structure of the universe on the grandest scales, carving out channels in the cosmic web and redistributing matter and energy over unimaginably vast distances. The very existence of galactic jets fundamentally changes our traditional understanding of black holes, transforming them from mere gravitational monsters into powerful cosmic engines capable of reshaping the very fabric of the universe. Deep in the heart of the Phoenix Cluster, one black hole demonstrates how radio jets can sterilize entire galaxies. The Phoenix Cluster serves as a unique cosmic laboratory, providing an opportunity to understand how supermassive black holes can control the fate of entire galaxy clusters through their radio jets. This monumental galaxy cluster, located 5.7 billion light-years from Earth, contains some of the most extreme examples of black hole feedback ever recorded, revealing the terrifying potential of these monsters in regulating star formation over millions of light-years. At the very center of the Phoenix Cluster is the supermassive black hole Phoenix A, which generates radio jets extending millions of light-years in both directions. These jets carve out vast cavities in the hot gas that fills intergalactic space, creating low-density plasma bubbles that can be detected by radio telescopes on Earth. The energy required to create these cosmic bubbles is truly staggering. The central black hole of the Phoenix Cluster must eject approximately 10 to the 45th power joules of energy into its surroundings every second, which is equivalent to the energy output of 10 billion suns. This colossal energy is deposited into the intergalactic medium, heating it to temperatures exceeding 100 million degrees Fahrenheit. The radio jets emanating from Phoenix A create a feedback mechanism that regulates star formation throughout the cluster. The energy from the jets heats the gas between galaxies, preventing it from cooling and subsequently condensing into new stars. This process can completely halt star formation in galaxies across the cluster, leaving them filled with aging stars that gradually dim, without being replaced by young celestial bodies. What makes the Phoenix Cluster particularly terrifying is its demonstration of how black hole feedback can manifest on a cluster-wide scale. The radio jets from the central black hole affect not only the immediate surrounding galaxy, but also thousands of other galaxies scattered over millions of light-years. This represents a unique example of cosmic environmental control by a single supermassive black hole. The jets also generate pressure waves that propagate through the cluster's gas at speeds of thousands of miles per second. These powerful shock waves can stimulate star formation in some regions while completely suppressing it in others, effectively shaping the distribution of stellar populations throughout the cluster. The Phoenix Cluster vividly shows what could happen if our own galactic center became more active. If Sagittarius A were to begin producing jets similar to those observed in Phoenix A, the energy output could heat the gas throughout the Milky Way, potentially halting star formation across our entire galaxy. The radiation from such jets could also pose a direct threat to any planets within thousands of light-years. Perhaps most disturbing is the realization that the Phoenix Cluster may represent the future of all galaxy clusters. As supermassive black holes continue to grow and merge, they may eventually reach masses large enough to completely regulate the gas content of their host galaxies. This could lead to a universe filled with dead galaxy clusters where star formation has been permanently halted. The Phoenix Cluster convincingly demonstrates that black holes are not merely local threats, but universal forces capable of controlling the evolution of structure on the grandest scales in the universe. In the distant future, black holes will reach such impressive masses that they will be able to consume entire galaxy clusters. The ultimate fate of these cosmic objects in our universe appears before us as a truly terrifying cosmic story that will unfold over trillions of years. As the universe steadily expands and cools, stars will eventually cease to form, galaxies will merge, and the supermassive black holes at their centers will continue to grow, transforming into monstrous behemoths of unimaginable size and colossal power. Modern scientific models predict that supermassive black holes will continuously increase their mass through several key mechanisms. Galaxy mergers will inevitably lead to the amalgamation of their central black holes, thereby giving rise to even more massive cosmic giants. Gradual accretion, that is, the attraction and consumption of gas, dust, and even entire stars, will steadily increase their mass throughout boundless cosmic times. But the most significant factor will be that the expansion of the universe will eventually bring more and more matter within the reach of these gravitational titans. In the distant future, when the universe is 10 times its current age, the most gigantic black holes may possess masses that will be more than 100 trillion times that of our Sun. These astonishingly enormous black holes will have event horizons spanning light years, making them larger than many existing star systems. The gravitational influence of these monsters will extend for hundreds of thousands of light years, effectively controlling the dynamics of entire galaxy clusters. The growth of these future black holes will radically transform the structure of the universe. As they consume more and more matter, their gravitational influence will extend further and further, eventually reaching the point where they can capture and consume entire galaxies. This process will be slow but relentless, with galaxies spiraling into these cosmic monsters over hundreds of billions of years. The process of consumption will create accretion disks that will be significantly larger than current galaxy clusters, with temperatures and luminosities dwarfing anything we currently observe. These future grandiose consumptions will generate jets of relativistic plasma extending for billions of light years, creating a kind of cosmic death ray capable of sterilizing entire regions of the universe. Perhaps most terrifying is the realization that these future black holes will eventually merge with each other, generating gravitational wave signals of such colossal power that they could potentially rip the very fabric of spacetime. The collision of two astonishingly enormous black holes would release more energy than the Big Bang, creating ripples in spacetime that could fundamentally alter the properties of the universe. The ultimate endpoint of this growth process is the formation of a single black hole encompassing the entire universe, which will contain all matter and energy in the cosmos. This ultimate black hole would have an event horizon that would be larger than the current observable universe, representing the ultimate triumph of gravity over all other forces. The timescales involved in this cosmic evolution are virtually impossible to comprehend. The process will take longer than the current age of the universe, by millions or billions of times. Nevertheless, the inevitability of this outcome does not make it any less terrifying. The growth of future black holes represents the ultimate cosmic destiny, a future where the universe itself becomes a single, all-consuming monster that devours everything that ever existed. The universe may already contain black holes so massive they defy our understanding of physics itself. Astonishingly large black holes represent the theoretical upper limit of cosmic horror. These are monsters so massive that they challenge the very foundations of our understanding of gravity, space-time, and the structure of the universe. These hypothetical titans would weigh over 100 billion solar masses, making them larger than entire galaxy clusters and approaching the mass of the observable universe itself. The emergence of such cosmic giants would inevitably require formation mechanisms that go far beyond our current understanding. Traditional pathways for black hole mass accretion, driven by stellar evolution and galactic mergers, cannot explain the existence of objects of such colossal dimensions within the current age of the universe. These astonishingly large black holes would likely have to arise from the direct collapse of entire regions of the early universe, or through some exotic processes in which dark matter and dark energy play a key role. The event horizon of such an incredibly enormous black hole, with a mass reaching 1 trillion solar masses, would extend for over 100 light years, surpassing in scale the distance between our Sun and the nearest star. The gravitational field of such a monster would be so colossal that it could hold entire galaxy clusters, causing thousands of star systems to orbit around it like cosmic particles in a giant atom. Tidal forces in the vicinity of these monsters would operate on galactic scales. Individual galaxies approaching an astonishingly large black hole would be stretched and distorted by these tidal forces, forming streams of stars and gas that would spiral into the monster's accretion disk. This process would be visible as the gradual destruction of galactic structure over millions of light years. The accretion disk around such an overwhelmingly large black hole would represent a cosmic structure unparalleled in the modern universe. Spanning hundreds of thousands of light years and containing a mass equivalent to millions of galaxies, this disk would glow with the intensity of quadrillions of suns. The magnetic fields generated by such a disk would be powerful enough to accelerate particles to energies approaching the theoretical limits of physics. Perhaps most disturbing is the assumption that astonishingly large black holes may already exist in the current universe, hidden in those regions of space where their influence has not yet been detected. These monsters could be lurking in the cosmic web, masquerading as concentrations of dark matter, or hiding behind the cosmic microwave background radiation. The discovery of astonishingly large black holes would revolutionize our understanding of cosmology and fundamental physics. Objects of such grand dimensions would allow us to explore the limits of general relativity, potentially revealing new physics that governs the behavior of matter and energy on the largest scales. The gravitational waves produced by the merger of astonishingly large black holes would carry energies that could influence the expansion of the universe itself. These cosmic collisions may be responsible for some mysterious aspects of dark energy and the accelerating expansion of space. The existence of astonishingly large black holes would also raise profound questions about the ultimate fate of the universe. If such monsters already exist, they may represent the future state of all matter and energy in the cosmos. These theoretical titans embody the absolute pinnacle of cosmic horror, objects so massive and powerful that they transcend our current understanding of reality itself. Black holes will outlive stars, galaxies, and perhaps the universe itself in a cosmic game of survival. The connection between black holes and the heat death of the universe represents the ultimate cosmic horror story. It is a tale of eternal predators that will exist long after every star has burned out and every galaxy has faded into darkness. As the universe moves relentlessly towards maximum entropy and thermal equilibrium, black holes will continue to grow, merge, and dominate the cosmos for timescales that make the current age of the universe seem like a fleeting moment. In the distant future, when the universe is 100 quadrillion years old, star formation will have completely ceased. The last red dwarfs will have exhausted their nuclear fuel and transformed into cold, white dwarf remnants. Galaxies will merge into massive elliptical systems, and the only remaining sources of energy will be the occasional collisions of dead stars and the slow consumption by supermassive black holes. In this grim epic of cosmic history, black holes will assume the role of the dominant form of matter throughout all creation. They will relentlessly increase in size, absorbing cold gas clouds, cosmic dust, and stellar remnants, gradually consuming everything in their immediate vicinity. The mergers of these colossal objects will generate gravitational wave signals that will become the only form of energetic activity emanating from the slowly fading universe. Nevertheless, black holes themselves will begin to slowly evaporate due to Hawking radiation, an astonishing quantum mechanical phenomenon in which they gradually lose energy, radiating it back into the surrounding space. However, it should be noted that this evaporation process proceeds at an incredibly slow rate for large black holes. For example, a black hole with the mass of our Sun would require a colossal 10 to the 67th power years to completely disappear, while supermassive black holes could exist for 10 to the 100th power years and even longer. This means that black holes will exist trillions and trillions of times longer than the universe as we know it. They will reside in a cosmic space where protons have already decayed, where the cosmic microwave background radiation has cooled to absolute zero, and where the expansion of space has carried all matter to distances measured in light years. The evaporation of black holes through Hawking radiation will be the last source of energy available in the universe. As these cosmic giants slowly shrink, they will emit particles and various types of radiation that will briefly illuminate the surrounding cosmic darkness. The smaller a black hole becomes, the faster its evaporation process accelerates, leading to a final explosive release of energy at the moment of its complete disappearance. Perhaps the most disturbing aspect is the hypothesis that black holes represent the universe's attempt to concentrate all matter and energy into the smallest possible volume, effectively reversing the expansion process that began with the Big Bang. Within this scenario, black holes are perceived not merely as random cosmic phenomena, but as fundamental elements of a universe that seeks to return to its primordial state. The ultimate fate of black holes may determine how the universe's existence will conclude, either by heat death with maximum entropy and a complete absence of available energy, or by a big crunch, where gravity ultimately overcomes expansion and everything collapses back into a single point. The interrelationship between black holes and cosmic destiny demonstrates these monsters not merely as local threats, but as powerful agents of the universe's ultimate transformation. In the last moments of the universe's existence, the final black holes will explode in bright flashes of Hawking radiation, marking the end of all things. The ultimate evaporation of black holes represents the absolute cosmic epilogue, the last chapter in the history of creation, where even these most resilient and powerful cosmic objects are finally forced to succumb to the relentless march of entropy. Thanks to Hawking radiation, black holes gradually lose their mass energy, returning it back into cosmic space, diminishing bit by bit until they disappear in powerful explosive flashes that will illuminate the dying universe one last time. This process originates from quantum fluctuations at the event horizon, where particle-antiparticle pairs spontaneously arise from the void. Under normal conditions, these pairs would instantly annihilate each other. However, in the immediate vicinity of a black hole, one particle can fall beyond the event horizon, while the other successfully escapes. This escaping particle carries away a tiny amount of the black hole's mass energy, causing it to imperceptibly shrink. For stellar mass black holes, this evaporation process is almost unimaginably slow. A black hole 10 times the mass of our Sun would require 10 to the 67th power years to completely evaporate. For most of this time, the black hole would emit radiation at a temperature barely above absolute zero, making it virtually undetectable against the cosmic background. But as a black hole shrinks in size, its temperature sharply increases. The final stages of evaporation occur at an astonishing rate. In the last second of its existence, a black hole will emit more energy than our Sun produces in its entire 10 billion-year lifespan. This final burst will create a flash of gamma rays, particles, and exotic radiation that will briefly outshine entire galaxies. While other cosmic phenomena have been capable of consuming entire galaxies, the last black holes to exist in the universe will be the most minuscule among them. These objects are relics of primordial cosmic monsters formed at the dawn of creation. Incredibly small in size, these microscopic black holes are comparable to atomic nuclei, yet their density is such that each harbors a mass comparable to mountain ranges. They will be the last witnesses to the fading of starlight, undergoing complete evaporation. Their final, catastrophic bursts will mark the absolute and irreversible end of ordered matter throughout the cosmos. When the last of the black holes completes its existence, dissipating into space, the universe will plunge into its final, unchanging state, an infinite, cold, dark, and empty expanse. Its vastness will be inhabited only by scattered elementary particles and diffused photons, devoid of any source of heat or light. Temperatures will drop to values extremely close to absolute zero, and the density of matter will reach such a minimal point that the probability of collision between individual particles will become negligible. This state is known as the heat death of the universe, symbolizing the ultimate triumph of entropy, all-consuming chaos over the order that once existed. However, perhaps the most intriguing and even somewhat unsettling aspect is the hypothesis that the process of black hole evaporation may not be an absolute end, but rather a grandiose transformation. All the information inexorably absorbed by these cosmic objects over countless eons of cosmic time will likely be released outwards at the moment of their final catastrophic explosions. This stream of data potentially contains a coded chronicle of everything that ever arose and existed in creation. Thus, the final act of the universe may turn out to be a massive unveiling of all its secrets, revealed to the world in a dazzling cascade of Hawking radiation. The true grandeur and, simultaneously, a certain horror associated with black holes lie not so much in their undeniable capacity for destruction, but in their unique function as custodians of universal memory. These enigmatic objects carefully preserve and accumulate information about every element they consume into their bottomless depths. Within their event horizons is sealed a detailed history of star formation, planetary evolution, and perhaps even the fates of entire extraterrestrial civilizations. At the moment the last of these colossal structures finally evaporates, it will inevitably release this colossal cosmic library back into the vastness of the universe, thereby erecting a grand final monument to everything that ever existed before the inevitable, all-encompassing darkness swallows absolutely everything. Friends, thanks for watching. See you in the next video.